In this video, I'm going to go over section 3.4 through the section 3.6. Okay, so from section 3.4, we're going to study specific the probability distribution functions. Okay, so but in chapter 3, we assume that I mean we deal with discrete random variable, right? So we're going to see the several popular probability mass functions. Okay, the first one is discrete uniform distribution. So discrete uniform distribution, you can see that the certain range, you know, probably in the interval. Okay, for example, 2 to 5. Okay, and then there are finite number of the outcomes. Okay, so here and then for each outcomes, the they have the equal probability. Okay, so now you see here, you can see that here's a definition of discrete uniform distribution. The random variable x has discrete uniform distribution if each of n values, so n is the number of outcomes in the sample space. Maybe you can say that, and then the in and then so saying that x sub 1 through x sub n has equal probability. So then, keep in mind this, the sum of all the probability, sum of probability in sample space must be equal to 1. To satisfy that, then what? Each of the I mean probability for each the outcome must be 1 over n, right? Because n times 1 over n equals 1, right? So now f of xi, f of xi means that what? The f is a probability mass function. Okay, so f of xi means that the probability of probability mass function of f at x is equal to xi. Here, the capital letter X means the random variable, and the xi denote I um, the outcome. Okay, or observations. Okay, so now it's the example 3.10. Serial numbers. The first digit of part serial number is equally likely to be any one of the digits 0 through 9. So then you can see that then what probability for each the the digit must be 1 over the 10, which is zero point 0.1, right? So if one part is selected randomly from a large batch and x is the first digit of the serial number, the x has a discrete uniform distribution with a probability zero point 0.1 for each value r. Okay, so 0 to 9. So f of x is equal to zero point 0.1. Yes, that makes sense, right? So now the see the mean and variance. Okay, so now here mean, this is the population mean, right? So now see, let me just look at this one. Okay, so suppose that the range of the discrete random variable x equal the consecutive integer a through the b. So we assume that the range in a discrete uniform distribution, the range is a through b. Okay, all right. So then the range of x contains b minus a plus 1 values. It makes sense, right? So for example, let's say b is a 5 and the a is 2. Then how many are discrete numbers there? So 5 minus 2 plus 1, right? So now values each with probability gonna be 1 over b minus a plus 1. So actually b minus a plus 1 is a number of outcomes in the range, right? So yeah, now we assume that what you see that the random variable x equals the consecutive integers. Okay, so that's why number of the outcomes in the range a comma b gonna be b minus a plus 1. All right, so now then b gonna be k equals a through b, and the k times 1 over b minus a plus 1. That must be equal to 1. Okay, so now then the now the what? I'm sorry, not equal to 1. Well, I was confused that. Then what? Using the definition of expected value of the discrete random variable, that's gonna be sigma, and then the k times the what? Um, f of f of k, right? So here f of k is 1 over b minus a plus 1 because in a discrete uniform distribution, the probability going to be 1 over n. Here, n is b minus a plus 1, right? So now, the what? So to simplify, we can simplify this, right? So let's explain about this one. I mean, the formula of the mean and variance by looking at my lecture note. All right, so now the okay, so why the mean of the mu? Okay, so mu expected value of the uniform discrete uniform distribution is b plus a over 2 because starting from this one, that's the definition of the expected value, right? And then definitely k equals 1 through 8 because range is either a through b, right? So now f of x is 1 over n. Here we figured out that what n is b minus a plus 1, right? So we got this one. We plug in 1 over b minus a plus 1 into f of x. And then since the 1 over b minus a plus 1 can be considered as constant because in the sigma, k is a moving index, right? So we bring out that fraction 1 over b minus a plus 1. So we're going to get this, that fraction times sigma k. So now then what? Then using, remember that I'm sure, I believe that you studied, you learned about the summation. I mean, sigma of the k is equal to um, the formula of the sigma of k, right? That's going to be using that formula of the sigma of k. K equals a through b is this b plus a times b minus a plus 1 over 2. Okay. So now then the let's see. Okay. So now then here's then we're gonna use that lemma. Okay. So sigma what k and k equals 1 through b is what b times b plus 1 over 2. Okay. Minus sigma k equals 1 through a minus 1 is what a minus 1 times a minus 1 plus 1, which is a over 2. Okay. So if you don't understand what I'm saying, please look at the study go just search the calculus 2 textbook, and then the summation the series part. Okay, go to the chapter series, and there is the formula about that sigma. Okay, so sigma, okay, you may learn this, k goes 1 through the n. Okay, that's in the from the calculus book. Okay, then k is equal to n times n plus 1, okay, divided by 2. Right, that's a formula, okay. But here, I'm just wanna figure out why this one is equal to that fraction. Okay, why that sigma, that expression can be written as like this question, right? So now I'm proving it. So using that formula, so that sigma expression is equal to this, right? And then that sigma is equal to that one. Okay. So see that sigma k equals 1 through b minus sigma k equals 1 through a minus 1. That's equal to what? Sigma k equals 1 through a through b, right? So we subtract the second, we gonna do difference. We're gonna do difference between two fraction. That's gonna be this, right? Okay. So now then subtracting two fraction, we're gonna get that one, this one. Okay. So now, because but this course, the focus on the introduction of the statistic and probability. Okay, this course doesn't focus on the theorem and the proof of um, the mathematical just formulas. Okay, you're gonna mathematical statistic. You're gonna take that course the next semester. That course focus on the more advanced mathematical background, the statistics and probability. So you're gonna learn more about the proof and the theorems, that course. But this course just introduction to statistics probability. So I'm not gonna focus on the proof things. Okay. So now, anyway, so let me just I'll explain this one briefly. So making making a difference between two fractions, we're gonna get this finally. Okay, b plus a times b minus a plus 1 over 2. Yeah, so back to here. So the multiplying this one, you see that b minus a plus 1, this is a common factor of the here and here. So, canceling them out, we're gonna get what? B plus a over 2. Okay. Now, what about variance? The variance sigma square, variance is this, y. That's also uh, we starting from definition of the variance, which is ex squared minus e of x. E of x is mu, right? Expected value mu square. Okay, so please remember this. This is you're gonna use this one a lot. Okay, so please keep in mind please the memorize the what the definition of expected value and definition of variance. Keep in mind that. So e of x squared gonna be this, right? And then mu square, we just got the mu, right? Which is b plus a over 2. So b plus a over 2 square right here. Now, first one, 1 over b minus a plus 1, that's the constant, bring it out. And then, so this one can be expressed, similarly what we did in the proof of the mean. We're gonna express, just split up that a sigma as k goes 1 through b, k goes 1 through a minus 1. Okay. Now then what? The in a calculus, what we learned this one, right? That one. You may yeah, you should find this one in the calculus textbook. Okay. So now then applying this one into for each the sigma for each the summation term. Okay. Then you're gonna get this, and then simplify it. Yeah, it's a lot of some complicate the maybe it's, sure that this is complicated, but just simplifying this, then you will get that one, b minus a plus 1 squared over 12. Okay, so now just please, you don't have to fully understand, this one, but please figure out, understand how you get this one, starting from the definition of the variance, and then using the that formula, okay, with by and then with splitting the sigma that expression as this to sigma, then you get this one. Okay, so let's say examples. Example is quite simple. Okay, just try the problem ask you to find expected value and then the variance or standard deviations. Let the random variable x denote the number of 48 voice lines they are used at a particular time. Assume that x is discrete uniform random variable with a range of 0 to 48. So here a must be 0, b must be um, 48, right? So then expected value going to be a plus b or b plus a divided by 2, which is 24. And then the standard deviation going to be square root of b minus a plus 1 square minus 1 over 12. Okay, so it's not a big deal, right? So now then, and then see here, what? Look at this one. Equation 3.6 is more useful than it might first appear. What's equation 3.6? This one. Okay. Okay. For example, suppose that the discrete uniform random variable y has range 5 through 30. Okay, 5, 10, is it 15? Now you see that. Okay, then y equals 5x. Yeah, we can express y, random variable y, in terms of another random variable, 5 to x. Here, random variable x is range 1 through 6. It makes sense, right? Okay. So now the okay, why we have to express the random variable y in terms of the x, where x is a random variable whose range is 1 through 6, because to use this one, keep in mind this, to use the formulas, the random variable x in the discrete uniform, the discrete uniform random variable x must be on the consecutive integers. Consecutive integers. Okay. But when you look at the y random variable, this is a multiple of 5, right? It's not, these are not consecutive integers. So then how can we express these outcomes, okay? Uh, the values of random variable y in terms of the, you know, the random variable whose range is consecutive integers, this y equals 5x. And then now e of y, because y is 5x, then e of a what ax plus b is equal to what? A times e of x. Remember that? Because the expected value satisfy linearity. I told you what that means, linearity, right? So e of a x plus b is equal to a times e of x, right, plus b. Okay, right. So I introduced this one the last time, right? And then same thing, v of ax plus b, but variance doesn't satisfy linearity, but instead of that, constant term just gone. And then a becomes a square. Okay, a square, and then v of x. Okay, so keep in mind this. Okay, keep in mind those two really nice property. Anyway, so then e of y is 5 times e of x, and then we know the e of x. I mean, it's not a big deal, you know. So the time 5 times e of x is, you applying the formula, okay, right there. Oh, right here, this using this one. How can we apply that formula into the random variable x? Because here random variable x is what? Discrete uniform random variable, right? Okay, 1 through 6. So a is 1, b is 6. So 1 plus b over a plus b over 2, which is the 3.5 times 5, which is 70.5. And then yeah, v of y is 5 square times, which is 25 times, and the b minus a plus 1 square minus 1 over 12. Okay, so yeah, okay. So I'm sure that I'm sure that you find it doable, right? So now the example 3.12, proportion of voice lines. Let the random variable y denote the proportion of the 48 voice lines used at a particular time. At x denote the number of lines used at a particular time. Excuse me. The y is equal to x over 48. Therefore, it makes sense, right? Y is equal to x over 48 because proportion gonna be x over 48. X gonna be what? 1, 0, 1, 2, 3, something like that. Okay. So now then, let see. E of y, oops. E of y gonna be e of x over 48, which is 0.5, and the v of y gonna be v of x over 48 squared. Okay. Similar to what we did here. Yeah, we did that. Okay. So now the next one. Give me a second. Give me a second. So keep in mind this. When you once you figure out that that random variable is discrete uniform random variable, so you want to use this one, then keep in mind this. The random variable, that discrete uniform random variable must be uh, on consecutive integers. Okay, just keep in mind that. All right. So and then yeah, I'll just look at the 3.5 and 3.6. Okay, and then maybe 3.7 and 8. But anyways, these from here, we're gonna study several popular discrete, I mean, probably math functions. Okay, but when you the key point is once you read the problems, you need to figure out the what type of probability mass function you have to apply. Okay, is that random variable introduced in the problems? Is it is about the for example discrete uniform random variable, or other type of probability mass functions. Okay, so let's see. Next one is this. So it's a binomial distribution. Binomial distribution, you see here a lot of several examples given. Okay, let's see here. First one, flip a coin 10 times. So let X is the number of heads obtained. Look at this, flip a coin 10 times. It means that we do experiment, same experiment multi times, right? 10 times or maybe 100 times. And then what about the outcome? For each try, let me say a trial. For each trial, we're gonna expect only two outcomes, head and tail, right? Then let's see next example. One machine tool produces 1% defective parts. Let X is equal to number of defective parts in the next 25 parts produced. So for each produce can be considered a trial, okay? And then we expected only two outcomes, defective parts or non-defective parts, right? Only two outcomes, right? And then the each the what the each produce are this what independent. Okay, so going back to the first example, flipping coin. Think about this: flipping coin first time we got ahead. Suppose that, okay, and then the second trial, the probability that we got had will not be affected by the result of the first trial, right? So for each trial is independent. That kind of trial is called the Bernoulli trials. Let's see the my lecture note. So 3.5 here. First one, a trial is what's a binomial distribution? So trial is repeated n times. Okay, n is a finite integers. So key in mind is binomial distribution. Number of trial is fixed. Why does matter? Because we'll see other distribution. In that distribution, which is similar to binomial distribution, but number of the trials are not fixed. Okay. Anyway, trials are independent. So I told you in the first example, the flipping coin, each trials are independent, right? So the result of each trial is not if does not affect the other trials, right? And each trial has only two possible outcomes. It is called the Bernoulli trials. Okay, so the independent and then only two possible outcomes is called Bernoulli trials. Okay, let's say uh, those two possible outcomes is success and failure. Okay, now then PMF, this is a probability mass function of random variable x is this f of x is equal to, and what's this? The parenthesis and long parenthesis and nx, that's the combination. Okay, combination. Do you know combination and permutation? We learned it, right? So permutation is number of way. So n, I mean n combination x means the number of way to choose x out of n without regarding order. Okay, what about permutation? Permutation is a npx means the number of way to choose x items out of n items uh, with considering order. Okay, order matters. Okay, so p is what? P here, the p is the probability that we get success in each trials. Okay, so p to the x power times 1 minus p to the n minus x. Now, what is it? PMF, f of x. That f of x represent the probability that we get what? The x is a number of success, okay? Here, x is a number of success. See, we probability that we get x times of successes out of n trials, okay? So that's the meaning of f of x. Okay, for example, you flip the coin 10 times. What is the probability that you get head 2 times? Then considering that the getting head as success and then getting tail as failure, then we want to find then mathematically we can express that the f of 2, okay, because in the binomial distribution random variable x denote the number of successes. Okay, so f of 2 is equal to n is the total number of the trials you did, which is 10, x is 2, And then what's a P? P is the probability that you get ahead, right? For each trier. So what's the probability that you get ahead in one single trier? 1/2, right? So 1/2 to the second power, right? So if you are to follow that, so let me write right here. So f of 2, okay? So flipping coin 10 times, it means that n equals 10, okay? I want to figure out the probability that we get head. We get head 2 times, which means the x is 2. Keep in mind this Bernoulli trials, random variable x means that one number of success. Number of success. Number of success. Let me say s, okay? So now f of 2 is equal to combination, get 10, 2, okay? And then p is a 0.5, right? Because of p here, p in that example, p is the what? Probability that you get ahead, okay? So 0.5 to the second power, and then 1 minus 0.5 times 10 minus 2, okay? Yeah, definitely x can be 0 through n, right? Because what's x? Random variable x is what? Number of success, okay? Now so I told you nx, this is ncx, okay? This is combination, okay? The definition of combination is this, right? But I told you can figure out ncx using calculator, okay? So then give me a second. So I'll show you how to calculate the permutation and the combination using calculator. I'm going to use TI-84 plus, but I'm sure that TI-83 and TI-4 is extremely similar. But TI-89, you have to search, okay? So how to do that. So now then, but I'm sure that most of people has TI-84 or plus, okay? So now here we go to the math, okay? Then you can see that, excuse me, there are 4 tabs, right? Math and then number and this is complex, okay? And then this is PRB means probability, okay? So PRB stands for probability. So we go to the PRB tab. Then you can see that there is what? The NPR right there, number 2 NPR, and then number 3 is NCR. The exclamation mark is a factorial. Okay, so before the enter the NCR, let me just get out of here. And so let's figure out the 10C 2. Okay, so first you have to enter the N. Okay, total number of items. Okay, here total number of the trials, right? And then we go to the math, and then we go to probability tab, and then here NCR is clear. Enter the NCR. Choose NCR, choose the and select the NCR and then enter 2. 2 is R, okay, and then enter. Then you get 45, okay. The more nice thing is this, you could, there is a way to calculate the binomial distribution, probability mass function of the binomial distribution. Do you see here distribution right there? Here, distribution, we go to that one. So press second and then VARs, okay. Then a whole bunch of the distributions, probability distribution functions right here. So we see that here, binomial PDF, binomial CDF. PDF means that probability density function, okay, and the CDF means a cumulative density function, okay. So we haven't seen the CDF, right? Cumulative probability function, right? So when you want to find the probability that x is less than y equals something, you gotta use a CDF. But now in this example, we want to figure out f of 2, which means that find a probability that x equals 2, which means that we want to figure out probability that number of successes is 2. Okay, then you use a PDF. So enter. So trial is a 10, and the p is the probability of success, right, at single trials, which is 0.5. Okay, X value 2, and then paste. Then you're gonna get this 0.043. Yeah, so normally we um, express the when you express the probability, we can get the up to 3 significant digit. Significant digit means that non-zero decimal number. Okay, so we don't count to 0. Okay, and then 439 here. Next number is 4, right? 4. And then we got, when you round up, we're gonna drop all the number from 4. Okay, so 0.0439. That's gonna be probability. Okay. So what about this? I want to figure out the probability that PMF, okay, uh, that the number of, I mean, just assuming that we just flip the coin 10 times, and then I want to figure out the probability that X is less than or equals 2. It means that I want to figure out the probability that we get head at most 2. Maybe we get 0 head, 1 head, or 2. Okay, we can head 2 times, right? Up to at most 2. Then we use binomial CDF. Okay, so number trial 10, P is 0.5, and then X value gonna be 2. Okay, and then paste. So now we see that definitely CDF must be, the must be greater than PDF. It makes sense, right? This is 0.04. This is 0.054. Okay, all right. So now, so you this is how to decalculate the binomial distribution. I mean, probability mass function of binomial distribution using calculator, and then you learned how to calculate the combination and permutation using calculator. All right, back to the textbook, and then so yeah, we haven't seen yeah, we saw the probability mass function of binomial distribution, right? So but um let's take a look at this one. I mean, again, so why the definition of PMF, probability mass function binomial distribution, is this? You may okay, so you may understand that p to the x power is a means that we just since we want to figure out the probability that we get the x, that much of the many of the successes, so p to the x power makes sense, and then 1 minus p represent probability failure. How many we're gonna get the failure out of n trials, n minus x times. So 1 minus p to the n minus x. That makes sense. What about why? What about this? That combination? Why the combination is involved? You may understand that one by looking at the example 3.13. These three channels. Okay, so let's see. Yeah, so the chance that a bit transmitted through a digital transmission channel is received in errors is 0.1. Also, I'll assume that the transmission trials are independent. Okay, so it should be each trial must be Bernoulli trial, right? Let x equals the number of bits in errors in the next 4 bits transmitted. Determine probability x equals 2. So there are the the sequence of 4 transmission, right? Bit transmission, right? So now then there's only two outcomes, two possible outcomes for each transmission, right? Error or not okay, not error, right? So now then we can think about how many possibles, how many combination of for that sequence. This, look at this table. So maybe all four bit transmissions, they are okay. O means letter O means okay. Okay, E means error. Okay, maybe first three bit transmission is okay, but last one we got error. Okay, whereas first two is okay, the third one we got error, and then last one is okay. So doing that, this is all possible uh, cases of the sequences. Okay, right here. So now then the X is a number of successes. I know it sounds weird, but let's say the success means that we got error. Okay. So first outcome, 0, right? Second outcome, we got one success. It means one errors. Okay. So now we count error for each possible outcomes. Okay. Now the event that X equals 2 consists of the 6 outcomes, right? So we're gonna find outcomes containing two errors, X equals 2, which is 6 outcomes. Okay. So now, I mean, so using the assumption that the trials are independent, the probability of EEOO is P of E times P of E times P of O times P of O, which is a 0.1 square times 0.9 square. But not only, that outcome, but also every single outcome in that event, they're probably going to be same as this 0.0081. Okay, so how many outcomes event? E 6 event here, 6, right? So probability x equals 2 going to be 6 times 0.0081. Now how did you get the 6? That 6 is what? Yeah, we get the manual. We just, we figure out all the possible outcomes, and then we found the outcome in here. We found the outcomes containing two letter E, right? But actually, that's nothing but the what? The 6 is not. We can get 6 by doing that. And what? The what? 4C2. Okay, this is nothing but the number of way to choose two bit transmission out of 4 without considering uh, uh, uh without considering what the order. Okay, so now then let me see. Let's see. Give me a second. So oh yeah, right here. So now so that's what we got for x. I mean generalized. We got this. I mean yeah. So 4 2 is 4 factorial over yeah. So you don't have to yeah. Mm, yeah, I recommend you memorize the formula of the combination. That's good. Okay, but even you don't memorize it, it's okay because you can figure out this one by using calculator. Okay. So now then, mm, now let me see this one. Next one. So example 3.15. Look at this. I explained that when I tell you how to use calculator, okay, to figure out the PMF or binomial distribution. But if we look at this one, probability x is greater than or equals 4. Okay, so that is equal to, you can, you know, let's take a look at the problem first. Okay, each sample of the water, this is example 315, okay, organic pollution. Each sample of water has a 10% chance of the containing a particular organic pollutant. Let's assume that the samples are independent with regard to the presence of the pollutant. Find the probability that in the next 18 samples, exactly two contain the pollutant. Okay, so 18 samples can be considered what number of trials. Okay, the two contains exactly two contains the pollutant. Two means the number of successes. I know it sounds weird that let's say the success represent the what it contains the pollutant. Okay, so and that's actually the number of samples that contain the pollutant in the next 18 samples analyzed. Okay, the x is the binomial random variable. Yes, makes sense. And the p is 0.1. Why? Where that comes from? Each sample water has 10% chance of the containing a particular organic pollutant. So 10% out of what? This is the actually what? The 10% means that for each sample of water, so this is the probability that we get particular organic pollutant in a single single sample. Okay, so that's why the p is equal to 10%, which is 0.1, and the n is 18. Yes. Now then, when you find out probability x is greater than 4, which means that determine the probability that at least 4 samples. You see the at least 4 samples. Okay, it means that x can be 5, 6, 7, 8, up to 18, right? So we have to find the probability that x is greater than or equals 4. Then that's gonna be what to this one p. We have to calculate p probability that x equals 4, x equals 5, plus x equals 6, plus 7, plus 8, plus, right? So it's a sigma x goes 4 through 18. That's too much. Okay. So then the easier way, see the easier way to calculate this one using complementary, rule for complement. Okay, 1 minus probability that x is less than 4. X is less than 4 means that what? 0, 1, 2, 3. Okay, so we get this. The best way is what? Well, using the calculator, right? So using the binomial CDF. Okay, so 1 minus, okay, so 1 minus binomial CDF. Okay, should so I'll show you. Give me a second. So right here, okay, so we go to the binomial CDF. Okay, binomial CDF. All right. What we want to find out, we want to find the probability that x is less than 4. That is means probability that x is less than or equals 3. Okay, because x is discrete random variable 0, 1, 2, 3, 4. Okay, so x is less than 4. The x can be 3.5. No, here the x is a number of success. Okay, so it should be positive integer. Okay, within the range of the number of the trials. Okay, so the we're gonna find that probability that x is less than or equals 3. Okay, so total number of trials is 8. Probability of success is 0.1, and the x is 3. Okay, so we got this. And then we're gonna subtract that one from 1. Okay, 1 minus, because we want to find the probability that x is greater than or equals 4. So we subtract that one from 1 using, because we are using the complementary, okay, the rule for complement. Okay, 1 minus the answer. So we got 0.08, 0.0981. Okay, so we're simply saying the 0.0982. But in textbook, they just they round off the third decimal place, so they got the 0.098. Okay, so the next problem is this. The next problem we see is to determine the probability that x is greater than or equals 3 and less than 7. Keep in mind that 3 is included, 7 is not included. And to figure out that, we're gonna use rule for complementary, rule for complement. Okay, so here, this is equal to, see, you can say this is equal to, you say, yeah, you can just calculate what textbook suggest. Okay, but or you can say this one the 1 minus probability that x is less than 7, okay, minus probability that x is less than 2. Okay, so x is less than 7 means that x is less than or equals 6. X is less than or equals 2. Sorry, equals 2. Okay, see. So we're gonna we figure out this one using binomial CDF. We figure out this one using binomial CDF. Okay. All right. Does make sense? Okay. So I'm not gonna do that. Please do this one by yourself. Okay. That you should get the same answer. Okay. So now next one is what's the mean and expected value and variance of binomial distribution. The conclusion, in conclusion, this uh, the mean expected value of the binomial distribution is n times p, and the variance is going to be n times p times q. What's a q? Q is 1 minus p. Okay, so then here's a proof. Okay, you see, let me see proof. in my lecture note. All right, here's my lecture note. I'm going to prove the expected value and variance of the binomial distribution. Okay, so there are two ways to prove that. Okay, so method one is followed by the textbook. Okay, and then method two is more um, mathematical way. Okay, so to show that the expected value and variance of the binomial distribution. Okay, let's see the first method. Define new random variable x sub I. Okay, x sub I is equal to 1 if ith trial is a success, otherwise 0. All right, so then what? Xi, the new random variable x sub I has can have only two value, or 1 or 0. By the way, how many random variables we have? N. Okay, you see that x sub I, for each trial we define a new random variable. Okay, returning 1 if ith trial is a success, or 0 otherwise. Okay, so binomial random variable x going to be what? Sigma of xi. Okay, for example, in 10 trials, first 2 trials we got success, then x sub 1, x sub 2 going to be 1, then the total number of success going to be 2, can be interpreted as what? Binomial random variable x is equal to sigma xi, I goes 1 through n. Okay, it makes sense, right? So you need to fully understand the what that means, xi. What's the relationship between the binomial random variable x and x sub I? For each trials, we define new random variable x sub y. Okay, x sub 1, x sub 2, x sub 3 through the x sub n. Okay, each x of I can have has a two possible random variable. Okay, two possible value, 1 over 0. Now e of xi going to be 1 times p plus 0 times 1. It makes sense, right? Does it make sense? Sigma, you see, do you remember that? The definition of expected value, sigma, and then the xi times probability of success. Okay, probability of xi, right? So this is 1 times p. 1 is the value of xi, x of I. Okay, p is probability that you get 1. The 0 is the another value of x of y, and the probability that you get 0 is what? Probability of failure, which is 1 minus p. So we got p. E of x going to be e of sigma xi, and then what? E of sigma xi is equal to what? Sigma of e of xi. It makes sense, right? So now, oh, yeah, so we'll prove this in, yeah, chapter 5. Yeah, we'll prove this one in chapter 5, okay? So E of the sum of the random variables is equal to sigma of the sum of the E of each random variables, okay? We'll prove that. So we just offset that, and then what? E of xi gonna be n times p. That's why the expected value of binomial random variable gonna be n times p. And the v of xi is e of xi times mu I squared, right? So mu sub I. This is mu sub I. Okay. So or you can say expected value of e of xi. Okay, we just got it. This one what? N times p, right? And this is p, right? This is p. Okay. The e of xi squared is a 1 squared times p plus 0 squared times 1 minus p. Yes. Okay. Let's simplify this. We're gonna get p times q. And the v of x is gonna be what? Then v of sigma xi. Oh, so this one also is equal to sigma v of xi. Okay. So this is n times p times q. Because v of xi is a p times q. How many are we gonna get p times q? N times, because I goes 1 through, I moves from 1 to n. So n times p times q. So now let's prove. Okay. So the second method is this. Starting from definition of e of x. Okay. Then what's f of x? Probability that we get x, right? But f of x is actually PMF, or binomial random variable x. We know the formula, which is a combination nx, p to the x bar, q to the n minus x. Right? Now, what is the nx? Is n factorial over x factorial times n minus x factorial. Okay. Now we're gonna see what we put the x in the top. Understood that? Actually, x factorial is what? X factorial is x times, right? And the x minus 1 times through the what? 1, right? So that x, we will cancel that out with that x. What is this? What's the rest of terms? That is equal to what? X minus 1 factorial, right? X minus 1 factorial. Okay, so that's how we got this. Okay, so now next one, move on. So starting from here, now then you see that we just take out n from n factorial, take out p from p to the x power. Then you're going to get that fractions. N minus 1 factorial over x minus 1 factorial, n minus x factorial, and then you see. So this is what actually, let me see. Now that's actually this one is actually what? Probably mass function of new random variable defined by x minus 1. And if you just define the random variable, u random variable z as x minus 1, then while z gonna move from 0 to the n minus 1 while x is moving from 1 to n. This makes sense, right? Okay. So x is moving from 1 to n, so then z gonna move from 0 to n minus 1. So we're gonna completely change a variable in a calculus too, integration. We're gonna change variable x to z. Okay, so z gonna be 0 to n minus 1, and the x minus 1 factor gonna be z factorial, and then n minus x factorial gonna be n minus 1 minus z factorial, and then p to the z power and the q to the n minus 1 minus z. Okay, so then this gonna be what? N minus 1. This is gonna be what? N minus 1 z. I mean combination of n combination of, I mean the nc z, right? N minus 1 cz. I'm sorry. Okay. So now we got this, right? Okay, this one right here. But that is equal to what? P plus q to the n minus 1. Why? Because that is definition of binomial expansion. Okay. So what's binomial expansion? You see that one in the textbook. In textbook, briefly mention about this, but binomial expansion is a plus b to the nth power is equal to sigma combination nk a to the k's power times b to the n minus k. This is exactly the same as what? This one. Let's see. That is exactly the same as definition of what? PMF, probably mass function of binomial random variable, right? Anyway, so using that binomial expansion, we can express this one as p plus q to the n minus 1. But by the way, what's p plus q? 1, right? P is a probability of success, and q is probability of failure on one single trials. Should be 1 to the n minus 1, 1. So we can just cancel it out. So we got n times p. Okay, so now I'll prove it. Okay, so the that's the proof of the expected value of random variable binomial distribution. Okay, the alternative way. Okay, so it may just hard to understand this, but if you I suggest you try to understand this proof, because you're gonna see this proof in I told you next the course in next semester, mathematical statistics. All right, so now let's see, give me a second. We move to the section 3.6, okay, geometric and negative binomial distributions. All right, so what's the geometry? Geometry is similar to binomial distribution, but number of trials is not fixed. Okay, geometry distribution is this: random variable x in geometry distribution is number of trials until we get a first success. Okay, keep in mind this: binomial distributions, the random variable x represent the number of successes, and then total number of trials fixed. But geometric distribution, total number of trials are not fixed. Instead of that, the trials are, you see that trials are conducted until a first success is obtained. Okay, so we deal with the Bernoulli trials, which is same as the binary distribution. Okay, so you see, random variable x denote the number of trials until the first success is obtained. Yes, I told you. Then PMF gonna be 1 minus p to the x minus 1. Now you see that times p, because we why the f of PMF gonna be like this? Because what? Because we assume that what? Because since the random variable x denote the number try until the first success is obtained, so we assume that we got only one success. So in the definition of PMF binary distribution, do we drop the combination? We don't need it, okay, because there is only one success, right? And then we just got the p, not p to the something, no. Okay, so 1 minus p to the x minus 1. So p times q times x to the 1, x minus to the x minus 1. Okay, so we'll see. But by the way, so you see that here, this is the 1 minus p to the x minus 1. This is the what? Geometry uh, can be considered the geometric series, kind of, if there is a sigma right there. Okay, so 1 minus p to the x minus 1 will decrease. Okay, if this is decrease, right here, decrease right here, the f of x will decrease, right, as x is increased. Okay, so we can expect that. But anyway, so let's see example 3.17 and 3.18. All right, let's see example 3.17, digital channel. All right, so you see the probability that a bit transmitted through a digital transmission channel is received in error is 0.1. So yeah, so it's p of success is going to be 0.1. I know it sounds weird, but assume that the transmissions are independent event. So it means that trials are Bernoulli trials, and then let the random variable x denote the number of bit transmit until the first errors. This is the major difference between the problems and then the previous example of what we saw in binomial distribution, right? So then x equals 5. What that means? That means the probability that we get uh, in the first error in fifth trials. Okay, so this is the probability the first 4 bits are transmitted correctly, and the fifth bit is in error. Okay, so this event can be denoted as okay, 4 okay, and now then that means what? The probability that we probably failure can be 0.9, right? So 0.9 times 0.9 times 0.9, right? Times 0.1. Yeah, so it's not a big deal, right? So now the example 3.18, wafer contaminations. The probability that of a wafer contains a large particle of contamination is 0.01. So then if it is assumed that the wafers are independent, what is the probability that exactly 125 wafers need to be analyzed before a large particle is detected? So you see, exactly 125 wafers needed to be analyzed before a large particle is detected. So then I know it's the you may just misunderstand the problems. Okay, 125 wafer need to be analyzed before a large particle is detected. So that means 126th trial you get success. You may say that, but I think yeah. So in these problems, um, I think 120, we have to find the probability x equals 126. Yeah, so I think the author of this textbook did it wrong, maybe. So, but the thing is this. Okay, let me follow the solution of the textbook. Okay, so let's say 125th trial you get a success. It means that you the 125th wafer has the large particle. I mean, the large particle contaminations. Okay, so then that means what? Probability x equals 125. I mean, then probability you get the first try the first success the at the 125th gonna be this 0.99 to the 124 times 0.01. Okay, so what about mean and expected value and the variance? Look at this. um let's see, let me explain about this one using my lecture note. All right, so I just back to my lecture note. So first one, the mu. Okay, let me start from the definition of the expected value. Okay, sigma and the k goes 1 to infinity, right? Because there is no total number of trials is not fixed. So because we just keep going, okay, keep going until we get first success. Okay, we just keep um the experiment. Okay, doing experiment um until we get the first success. So k goes 1 to the infinity. Okay, times, and then what's PMF of the geometric distribution? P times P 1 minus P to the k minus 1, right? All right, now here, a second. So then what? Since give me a second, right here. Then P is what? P is a constant, right? Because K is a moving index, right? So we can bring out P, and the 1 minus P is actually Q, right? We can write it, the 1 minus P is Q. So we got this one, P times, okay? And then now K times Q to the K minus 1 is actually can be expressed as a derivative of Q to the K's power. Okay, so considering Q to the K's power as, I mean, considering the K times Q to the K minus 1 as, for example, let's say this is a definition of function G of Q. That's Q. Give me a second. Not G of Q. So let's consider this one as a definition of function. What letter do we use? The F? No. Yeah, H. Okay. H of Q. H of Q. Okay. Right. So now let's say this is the function, definition of function, and then the prime, H prime. Okay, derivative of H of Q is K times Q to the K minus 1. Okay, but what's the entire derivative of K times Q to the K minus 1 with respect to Q? Q to the K's power, right? Okay, so we could express K times Q to the K minus 1 as a derivative of Q to the K's power with respect to Q. Okay, now the sigma satisfies the linearity. So the sum of derivative Q to the K's power is equal to what? Derivative of the sum of Q to the K's power. So we can bring out the differential operator dq outside of the sigma. Okay. Now then, what? This is what? Geometric series. Because Q is less than 1. Q represents probability of failure. Probability must be less than 1, right? I mean, yeah, less than or equals 1, right? Okay, but obviously Q must be less than 1, right? So now then, since the Q is less than 1, so that geometric series must converge. Okay, Q that is equal to, you see that here? This is a geometric series, and since the absolute value of Q is less than 1, so it converges Q over 1 minus Q. Okay, but if you don't get it here, please go back to the series in calculus 2. Okay, so now then we got this P times derivative Q over 1 minus Q. What's the derivative Q over 1 minus Q with respect to Q? this using the what the what the quotient rule for derivative. Okay, so then we're gonna get, and then also 1 minus q plus q gonna be 1 because minus q plus q is gone, and then 1 minus q is nothing but p. So p times 1 over p squared, which is 1 over p. Proof is done. So that's the 1 minus p. That's the what expected value of geometric distributions. Okay. So now next one, what about the variance? Okay, variance gonna be 1 minus p or p squared. Okay. So yeah, so now I'm not going to prove this one right now, okay? Because once we study the moment of generating functions, then I'll prove this, okay? So now see the lack of memory property. Please read the paragraph in the textbook, lack of memory property, okay? The in the bottom of the 3 point beneath the 3.19 and 3.20, okay? So now see. And then give me a second. 3.19 is about the finding the expect value and then variance of the geometric series. Simply you just apply the formula 1 over p and then 1 minus p over p squared. Okay. So now then give me a second. And the negative binomial distributions. What's a negative distribution or actual negative binomial distribution typo? It should be binomial right there. So this is a generalization of the geometric distribution, in which the random variable is the number of Bernoulli trials required to obtain R successes, result in the negative binomial distribution. Okay, so give me a second. Give me a second right here. So let me just first one. Let me recap what we have learned in the binomial distributions, the geometric distributions. The key difference between binomial distribution and geometric distribution was what? The binomial distribution number of trials is fixed, total number of trials is fixed, and then random variable x denote the number of success out of n trials. But geometric distributions, the total number of trials is not fixed, and then the random variable x denote the number of the trials until we get first success. And the negative binomial distributions, okay, so negative binary distribution, random variable x, still the total number of success is not fixed, and then the random variable x denote the what? The number of trials until we get R successes. Okay, so see example 3.21 digital channel. I think you just became just really familiar. You're just really familiar with that problem, right? So probability that a bit transmitted through a digital transmission channel is received in error is 0.1. Okay, so we have two outcomes: okay or error, right? So uh, the the what digital channel is transmitted correctly. That means okay, and then we got error not correctly. That means we got errors. Okay, so assume that the transmissions are independent event, and then let random variable x denote the number of bit transmit until force error. Okay, so now then see. Now this example of lack of memory property. So now this one, let's see, I think, give me a second. All right, so right here. Then the R gonna be R means what the number of successes. Okay, 4. Okay, and then in the example 3.21, so X gonna be 10. Okay, so now give me a second. Here, see the R successes. So in the example 3.1, R should be 4, right? And the problem says that for example, P probability that we got what X equals 10, it means that we need 10, we got for the success when we do the 10 trials. Okay, so that means that's a question. Okay, find out p of x equals 10. Okay, so what that means, the probability x equals 10 and the r is 4. It means that we probability that we get four errors, and then the give me a second. So give me a second. I need to look at the examples. Yeah, so p of x equals 10 means the probability that exactly 3 errors occur in the first 9 trials. And then the last trial, 10th trial, we get the fourth error. That's the meaning, that's the meaning of p of x equals 10. And then we need to find out p of x equals 10. Okay. So then, so but look at this one, Lego memory property, example 3.17, the explanation of this one. Example 3.17, the lecture, please look at by yourself. Okay. So now then, to find the x equals 10, first we have to calculate what the probability that what we get 3 errors until nine trials, right? That's nothing but what the binomial distribution, right? So this is going to be 9 combination 9 3 and the 0.1 to the third power, 0.9 to 6 power. Okay, so you see that, which means the probability exactly 3 errors occur in the first 9 trials. This is a binary distribution. And then last trial, 10th trials, then what we get the fourth errors. 0.1, right? 0.1. Okay. So now the doing this, we're gonna get this. And then 9 3, where we got 9 3? Generalize this one. 9 is actually x minus 1. X is the number of trials until we get our successes. And then 3 is r minus 1. And the 0.1 is p. And then this 3 is what? R. Um, and then point is r minus 1, right? But we're going to get the one more term, 0.1. So eventually we're going to get the 0.1 to the fourth power. So r, that's why we got r right here. And then 0.966 comes from what? X minus r, right? So we got this. That's the PMF, probability mass function of negative binary distributions. Okay, so how we got this? The what? How we get this? Because from here, binomial distribution, PMF binomial distribution of x minus 1 and r minus 1. Okay, so out of x minus 1 trials, probability that we get r minus 1 successes, that's a binomial distribution, right? Times p. That's going to be binomial, a negative binomial distribution. So summarize this, we can get this. In a series of binomial trials, independent trials with a constant probability p, okay, of success. The random variable x is equal to number of trials until r successes occur. If r equals 1, that negative binomial distribution is exactly the same as the geometric distribution. Okay, so x is a number of trials until r a success. Until occur is a negative binomial distribution, negative binomial random variable with p probable success. Okay, so and then PMF is this. Okay, so now the give me a second. So, or you could express the negative binary distribution in terms of the geometric distributions using lack of memory property. So I think I'm gonna we see here. If r equals 1, I told you negative binary distribution gonna be equal to geometric binary distribution. Second one, think about this. Think about the negative binary distribution with r equals 3, and then what the x is 12. So it means that we get the x is 12 means that we get the we got the 12 trials until 3 successes. Okay, so maybe, for example, we get the first trial in the fourth trials, and then we get the second trial in the 10th trials. We get the third errors in the 12th trials, right? Now here we're gonna break up that trials into the you know uh, three groups kind of, okay? So 1 through 4, and then 5 through the 10, and then 11, 12, okay? So now the dot indicates trial that result in a success, okay? So now then the x, which is number of success until uh, r, in this example, 3 successes, we get 3 successes can be expressed as x1, x2, x3. But for each, now x sub 1 through x sub 3 represent the what? Geometric uh, geometric random variables. You see that in x1 is what is the random geometry random variable, which means that the number of trial until we get first success. Okay, is 4, right? And then now x2. Okay, so from here it's done here. And then for x2 is what? The number of trial until we get first trial again. Because here, even though we split out, x1, x2, x3 can be considered as independent random variables. Okay, so now then why? Because you know the even even though we get the error in the first trials, that does not affect on the what the probability to get the success in here in x2 of x2. Okay, so we can completely separate the x, that x is the render variable x1, render variable x2, render variable x3. Okay, and then for each random variables are what? For each random variables, it is what? Geometric random variable. So we apply geometric random variable x1, x2, x3. Okay, so now then for the x2 is what actually what can be interpreted as what? The number of the trial. I mean, we need 1, 2, 3, 4, 5, 6. X2 is a 6th trial, means that 6th trial until we get first success. X3 gonna be 2. Why? Because we got 2 trials until we get first success. Okay. Now then, yeah, so let x is the total number of trials required to obtain R successes. X1 is the number of trials required to obtain the first success, second through the R successes. Okay. So now then probability x equals R gonna be sigma probability x equals xk. Now what is this? Now this is what sum of probability of geometry random variable, because the reg of memory property. I told you what's the reg of memory property. Simply saying that, yeah, I told you each group x1, each random variable can be considered as independent, completely separate the geometry random variable. Okay, that's the reg of memory property. Please read the paragraph in the textbook about the reg of memory property by yourself. Okay, so now then. So now, binomial random variable and then negative random variable. I told you, binary random variable count the number of successes in the n binary trials, and it's fixed. Okay, so number of trials are predetermined. Number of the success is random. And then negative binary random variable is what? Count of number of trials required to obtain R successes. The number of the trials is random, and number of success is predetermined. Okay. And the mean and variance is this. The expected value of negative binary random variable is R or P, and then the variance of negative binary random variable is R times 1 minus P over P squared. Okay, so now let's see the example, the 3.22. Okay, so example 3.22, camera flashes. We haven't seen that example, I mean that experiment in example 3.1, but consider the time to recharge the flash in example 3.1. The probability that a camera passes the test is point A, and the camera performed independently. So what is the probability that the third failure is obtained in 5 or fewer tests? Okay, what is the probability that third failure is obtained? So R equals 3, right? Okay. And then number of trial is not fixed, not predetermined. Oh, so definitely this problem is not about binomial distribution. And then not first failure, but third failure. So this is not problem about geometric distribution. So that must be a negative binomial distribution. Okay, this is how you figure out what distribution, probability distribution you should apply. So now X is what? The number of trials in the number of the camera testing until we get 3 failure obtained, okay? Then the question, then we have to find the probability that X is less than or equals 5, okay? Right here. The sigma X goes 3 to 5, okay? So now then the X minus 1 over R is 2, right? R minus 1, R minus 1, 2, right? And then the P to the R's power, and then Q to the X minus R, okay? So you just calculate this. Then you may just wonder that can we calculate this one using calculator? If you have TI-89, yeah, you should have the that negative binomial distributions in the calculator. Yeah, you can use this one. But if you have TI-84 or 84 plus, um, that there is no function, intrinsic function for that one. Okay, but you may find the geometric distribution, geometric PDF, geometric CDF in your calculator, TI-84, TI-84 plus. Okay, so so now the X equals 3 to 5, it's not big deal, right? So when X equals 3, you can get 0.2 cube, and then when X equals 4, you got this one. When X equals 5, you're gonna get this. Okay. So, but yeah, so and then yeah, definitely you can calculate that combination using calculator. Okay. So, but the thing is this, you need to fully understand the difference between the binomial distribution, geometric distribution, and the negative binomial distribution. Okay. So let me stop here, and then I'll cover the this 3.7, 3.8 next time.